So the second method is the classical approach. So remember, with the empirical method, when do we use it? We use it when there's been some observations, right? So there's been a study done, there's been a survey done, something like that. That's when we use the empirical method. Now the classical method is going to be very similar to what we've already done. However, it's just a little trickier, and we'll see in the future a little bit why. All right, so we say that the classical approach of computing requires equally likely outcomes. Equally likely outcomes, which means that each outcome has the same probability of occurring. And specifically, when you break it down into the simple events, right? Each outcome, those have to all be equally likely. So if an experimenter has a number of equally likely outcomes, and a number of ways that event E can occur, then the probability is going to be as follows. So it's the number of ways E can occur over the number of possible outcomes. The number of ways E can occur divided by the number of possible outcomes. Now, you may be thinking, well, isn't that exactly what the empirical rule was? Wasn't it the number of ways E happened over the total number of ways? And it's very similar, yes. So, go back to what we talked about with events and simple events, right? When you have an event, that can occur with one or more outcome, right? So when we talked about the event of, if we had two coin flips, right? So two heads, two tails, and one heads and one tails, right? So if we talked about what's the probability of getting two heads, you may be thinking it would be 1 out of 3, right? There's 3 outcomes. You may also think, oh, well, it's 2 heads out of 2 tries. But in actuality, when you look at it, right, you have to look at all of the outcomes. So the 2 heads, we said, was heads, heads. The 2 tails is tails, tails. And the 1 head, 1 tails is either HT or TH, right? So in actuality, if you're trying to find the probability of 2 heads, well, there are 4 total outcomes, right? And there's only one of them that is 2 heads. So that's why this can get a little confusing. Let's do some more examples. All right, so a fair die is rolled. Fair dice means that each outcome is equally likely. The possible outcomes of this experiment can be written out easily. So what is the probability of rolling a 7? Well, if you have 2 dice, what are all the outcomes? So remember, dice goes from 1 to 6 and 1 to 6. So if you add those together, our outcomes would be 2, 3, 4, 5, all the way up to how much? 12, right? 1 plus 1, 6 plus 6. So, and actually we can just write them all out. It might be easier for us to see. So, would the probability of getting a 7 be 1 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11? Which would be, if we divide that out, that'd be about 0.091 if we round to 3 decimals. Is that how we would do it? Well, let's think about this. So Well, notice that we have not actually done anything, right? There's no study done, so we have to use the classical approach. And the classical approach says that everything has to have an equally likely chance. Do you have the same chance of getting a 2 as you do of getting a 3? Or we can even say this. Do you have the same chance of getting a 2 as you do of getting a 4? How can you get a 2 for 2 dice? So for a 2, it's because you rolled snake eyes, right? 2 ones. For a 4, however, how can you get a 4? Well, you could get a 1 and a 3. You could also get a 2 and a 2. And essentially, you can also get a 3 and a 1. But regardless, right? Do you have the same chances of getting a 2 and a 4? No, you do not, right? So this is going to be, so these outcomes essentially are the same as these, right? These are events that can be broken down further. So we need to make sure to break down our events even further than that. So this is the incorrect answer. It is not 1 out of 11. So we need to actually write out every single possibility. We need to break it up into its simple events. So, way we can do that, we can write out all of the, we can make a table, right? So, a die has 1, 2, 3, 4, 5, and 6. And we can just kind of make this table. All right. So if you have a 1 and a 1, you add those together, you get 2. 2 and 1, 3. 3 and 1, 4. 5, 6, 7. We can see on this side it's the same thing, right? 1 and 2 is 3. 4, 5, 6, 7. Then we have 2 and 2, which is 4. 3 and 2, which is 5. 6, 7, 8. And likewise, you go the other side. 5, 6, 7, 8. And you can start to see the pattern, right? So we got 6, 7, 8, 9, 7, 8, 9, 8, 9, 10, 9, 10, 10, 11, 11, 12. So now, in actuality, how many, so remember, going back, what is the probability of getting a 7? So these are all of the outcomes. And if we notice, there are 6 ways of getting a 7. Out of how many total outcomes are there? So 6 by 6, you can count them up or you can multiply, right? 6 times 6 is 36. There are 36 possibilities. So when we divide that out, we see that we get 0.167. And decimal form is probably going to be the best way of doing it. So if you have a decimal to 3 decimals, that's probably going to be the best way of doing probability. What's the probability of getting a 2 on a roll? Okay, so we've already seen it's out of 36. So how many ways can you get 2? Well, it's just this one way, right? So this 1 out of the 36 possibilities, which is about 0.028. So, in other words, in 36 rolls, we would expect how many 7s and how many 2s? Well, actually, we already said out of 36 rolls, we would expect 6 7s, right? It occurred 6 times. We could also multiply, right? So we could also multiply this decimal by 36. And we get 6.012, which is 6, right? And same thing with here. Out of 36, we would expect 1 roll. Or again, if you multiplied this decimal by 36, you would get 1.008, which again would be 1. So that's another reason why fractions are kind of good, right? Out of 36, 1. Let's look at another one. So problem number 5 on your handout. Sophia has 3 tickets to a concert, but Yolanda, Michael, Kevin, and Nisha all want to go to the concert with her. To be fair, Sophia wants to randomly select the 2 people who will go with her. So determine the sample space for the experiment. In other words, list out all the possibilities of sample size n, where n is 2. So doing sample space, let's make sure to have a brace, right? Have our braces. In other words, bracket. So what are all the possibilities of 2 people that can go with her? So we could have Yolanda and Michael go with her, Yolanda and Kevin, Yolanda and Nisha. So we could have Michael and Yolanda, but that's the same as Yolanda and Michael this time, right? So Michael and Kevin could go with her, Michael and Nisha could go with her, or Kevin and Nisha. So these are all the possibilities. So now, what is the probability that event Michael and Kevin attend the concert? So this one is Michael and Kevin. So that would be one possibility out of 1, 2, 3, 4, 5, 6, which is 0.167. Now, some of y'all might be asking, well, wait a minute. When we had the other method, right, when we had the coin tosses, how come heads and tails and heads were different, but in this case it's not? Well, that's a good question. In actuality, we can write out like this. So if we do write out like this, right, we could also have Michael and Yolanda, Kevin and Yolanda, Nisha and Yolanda, Kevin and Michael, Nisha and Michael, Nisha and Kevin, right? But if you actually see, nothing changes, because what we get is for Michael and Kevin, we would get 2 of them out of a total of 12, which is the exact same answer. So that's why we can kind of just delete all of them, because it would literally be the same thing. Whereas when it comes to here, right, if we have a heads and a tails and a tails, since there's only one way of doing it, it would be very different, right? So let's compute the probability that Nisha attends the concert. So how many ways does Nisha attend the concert? So Nisha can attend the concert with Yolanda, with Michael, or with Kevin. So there's 3 ways out of a total of 6, which if we divide that out, is 0.5. So if we conducted this experiment 100 times, about how many of the experiments would result in Nisha attending the concert? So remember, when we have the experiments 100 times, we just multiply the decimal by 100, and we would get 50. All right, last problem of this section. Suppose that a survey asked 500 families with 3 children to disclose the gender of their children and found that 180 of the families had 2 boys and 1 girl. Estimate the probability of having 2 boys and 1 girl in a 3-child family using the empirical method. So, using the empirical method means that we are looking at an observation. So the observation, right, 2 boys and 1 girl, was that it occurred 180 times out of 500 families. And when you divide that out, we get 0.36. Now, compute and interpret the probability of having 2 boys and 1 girl in a 3-person family using the classical method. So remember, the classical method is not using an observation. It's when all the outcomes are equally likely. So for 3 children, remember we had 8 options. So it was, if we can write them all out again, right? You can have, well, this is very similar to the ones that we did heads and tails, right? So you can have 3 boys, you can have 3 girls, You can have two boys and one girl where the girl is first, the girl is second, and the girl is third. And then you can have two girls and one boy where the boy is first, the boy is second, and the boy is third. And all of these have one way of occurring, so this is all equally likely. So how many ways can we have two boys and one girl? So we can see that that's 1, 2, 3 ways out of a total of 8, which gets us 0.375. So similar, right? And remember, if we use the law of large numbers, the more times we did this, right, the more families we looked at, the closer this probability, this proportion would be to the actual probability of 37.5%. So this is kind of what we were talking about at the very beginning. Using the empirical method is getting an approximation. Using the classical method, we're getting the actual answer. Subjective probability. So I just want to talk about this one time. We're never really going to talk about the subjective probability ever again, but we did need to talk about it because actually this is the one that everyone uses in their common day life. So this is the probability based on personal judgment. I guess without the E. So this is just gut feelings. So, for instance, this is like I said, this is the one that everyone uses every single day of their lives, basically. So, we can ask the question, for you as a student, what's the probability that you'll pass this class? Right? What's the probability you'll pass this class? So some students might say 70%. Some people might say 90%. They're going to put a lot of work into it. They're really good at math. Some people may say, oh, it's going to be very small, like 30%, maybe 20% if I'm lucky, right? Well, where are you getting these probabilities in your head, right? Have you done observations? So have you taken the class multiple times and you passed it and you failed it and you failed it and you passed it again and you passed it, right? And then we're taking the number of times we passed divided by the total number of times? Well, no, right? Hopefully if you've already passed the class, you're not taking this class again. So not the empirical method. And another one, what are the two outcomes that we can have? Well, you either pass or you fail. Are you equally likely of doing both of those? No, you're not, right? Let's just think about this. If you worked really hard on this class, right? Are you equally likely to pass as you are to fail? Hopefully not. Hopefully if you study and you do all the work and you watch all these videos, you're going to be more likely to pass. Then again, let's assume that you don't do anything, right? You're not even watching this video. So you just sign up for the class and you don't watch any of the videos, you don't do any of the homework. Are you equally likely to pass as you are to fail? No, you're almost certain to fail, right? If you do nothing. Because you're not learning anything. So that means that we cannot use the classical approach. So thus, you're just kind of doing a judgment, right? You're kind of thinking about how well do you do in math classes in the past, how much commitment you can make to this class, and that's what you're kind of basing it off of. So one last thing I wanted to say, and then we'll be done with this lesson completely. So just because you have two outcomes does not mean that you have a 50-50 chance of getting things, right? Here's a perfect example, right? Just because you have two options does not mean you have a 50-50 shot. So here is two examples. So One's a little more serious, and people say it all the time, and one is a little goofier. So let's think about winning the lottery. I have actually heard people say that you should always buy a ticket, right? Because you have a 50% chance of winning the lottery. Either you win or you lose. So you might as well buy a ticket because there's a 50% chance of winning. But I'm sure you can already see that that makes absolutely no sense, right? Otherwise, many people would be winning the lottery, right? So that doesn't make any sense at all. And the reason why is because there are way more losing tickets than there are winning tickets, right? There's only one winning ticket, but if 100 people buy tickets, then at the very least it's 1 out of 100, right? It's probably even less than that in actuality. But yeah, you can see that just because there's two options, winning and losing, there's a lot more ways to lose than there are to win, right? So again, two options is not necessarily 50% each. All right, let's do one last one, and this is a silly example that actually I heard in middle school. So in middle school, my band director was talking to the guys, and he said, hey, you should always ask out someone to go on a date because it's a 50% chance of them saying yes or no, so you might as well ask, right? Either they'll say yes or they'll say no. So 50% chance. Now, why a middle school band director was talking to children about dating, you know, who knows, but that's what he said. But if we think about this, right? Is there a 50% chance of the person actually saying yes to a date and saying no to a date? Is that equally likely? Well, as a middle school boy, if you don't shower and don't wear deodorant for a month, is the person equally likely to say yes than they are no? Absolutely not. Most people would say no, right? So you have more of a chance of them saying no than of yes. Now, I've had students say, well, maybe they're into that thing. Well, then, haha, I still got you. Then they're actually more likely to say yes than they are no. So either way, it's not a 50-50 shot, right? So once again, two options does not necessarily mean a 50-50 chance. All right, so that's it for the first lesson of basic probability. If you have any questions, as always, feel free to email me or contact me in any way you can. Have a great day.